Hi students, this is Mrs. Laybourne and this is section 11.6, Combinations. Combinations are selections from a set without regard to order. So for example, if we took the first letter of each of your first names, we have the set J, R, and Z. And that would be the same set as the set R, Z, and J. It's still the first letter of each of your first names. If we look at all the combinations of, let's say, taking those three letters, taking two of those three letters, we could have the set JR, we could have the set JZ, and we could have the set RZ. And thus we would have three different combinations. If we instead look at the permutations of each of these sets, then the set JR, if we're looking at permutations, it could be the set JR, or it could be the set RJ. And those two would be different if we're looking at permutations. But a combination, it's the same because the order isn't important. So for each of these sets, there would be two different ways of writing that set, made up of just two of the first letters of two of your names. And so if we're taking the number of combinations and I have three letters and I'm choosing only two of them, I'm going to get three possible, whoops, my pen's getting a little silly right now. Let me get that back, and we would have, whoops, let me see if I can get it to calm down a little bit here. I would have three possibilities, whereas in permutations I would have two times that number of 3 choose 2, and in other words, then the number of permutations is, in this case, 2 times the number of combinations. If we're looking at just notation here for a second, if we have the number of combinations of n objects and we're going to be looking at or choosing k of those objects where k is a number less than or equal to n, then we could write our, use this format to write the number of combinations of n objects taking k of them, or n choose k. And if we had just the number of combinations of n objects and we're going to choose all n of them, well, there'd be only one way to do that. In a similar way, if we want to have n and we want to choose only one letter, out of the n, then there would be, whoops, there would be n different ways to do that, because I would have n different letters and I could choose any one of the n. We also say that if we have n objects and we're choosing 0 of them, there is one way to do that, and that would be as if I have the empty set, or I'm not choosing any of the members of the n possible numbers or members. So if I move along, let's see if my pen will settle down a little bit. Let's suppose then that we look again at this formula. So if I have number of combinations of n objects, and I'm choosing k of them, or n choose k, that it is equal to the number of permutations of those n objects if I choose k, if I multiply it by k factorial. And the reason this is true is that n choose k is equal to the number of permutations of n objects, and I'm choosing k of those objects, divided by k factorial. Well, that's the same thing as, I wish this would straighten up a little bit for you, 1 over k factorial. Oops, let me fix that a little bit. That would be the same as 1 over k factorial times the number of permutations of n objects, and I'm selecting k of them. Well, that would be the same as 1 over k factorial, and then times, and we write for the permutations, we'd say it's n factorial divided by n minus k factorial, which is equal to, it's not cooperating very well, n factorial divided by k factorial times the quantity n minus k factorial. And another way of saying that would be to say that it's n times n minus 1 times n minus 2. If you could see how I'm having to lift up my pen, it's really kind of funny. Dot, dot, dot. And until we get to n minus the quantity k minus 1 all over k factorial. Okay, so we can also, let me insert another page here real quick. We can also use another notation as well, and we'll be studying this notation very soon with the binomial theorem, but we can use the binomial coefficient notation. And so if we write that notation, which would look like, let me just see if it would make a difference in the color. If I have 6 and 2, and I put them in parentheses like this, that's the binomial coefficient notation. And it is the same thing as saying 6, choose 2. Now, if you think about that, if I have 6 objects and I'm selecting 2 at a time, then it means that I'm not selecting 4 of them. So 6 choose 2 should give me and will give me the same results as having 6 choose 4. Or if I write it in the binomial coefficient notation, I would have 6, 4. It doesn't mean fraction, don't think that. There is no bar there. But it's just a quick notation so we can see, look at the different coefficients. And again, this 6 choose 2 would be 6 factorial divided by 2 factorial, as well as 6 minus 2, or 4 factorial. And that would be the same as 6 choose 4. We'd have 6 factorial over 4 factorial, and also 6 minus 4 factorial, or 2 factorial. And so I have the same product and quotient as I would for 6 choose 2. If we look at how many games, let's suppose we want to find out how many games can be played if we have 9 teams and each team is going to play all the other teams once. So I have 9 teams, and a team can't play it itself, so I have to choose 2. So 9 choose 2. And again, I could write it this way. And that would be equal to 9 times 8 all over 2 times 1, which would be 36. And if I had each of the teams playing all the other teams twice, it would just be 72 then. Let's suppose that you have 2 different parts to a test, and the first part has 10 questions, and you have to answer 7 of those. And in the second part, there are 5 questions to choose from, and you have to select 3 of them. So 3 of those parts have to be answered. So the number of different combinations, well, it would be 10 choose 7 times 5 choose 3. Well, again, that would be using the coefficient, binomial coefficient notation. That would be 10, 7 times 5, 3. Well, If I have 10 problems and I'm choosing 7 of those, then it means I'm not choosing 3 of them. And so that would be the same as saying 10, choose 3. Times again the 5, choose 3. Or using the binomial coefficient notation. And so that would be 10 times 9 times 8 divided by, I'll try to get it to write a little clearer, 3 times 2 times 1. And then that's multiplied by 5 times 4 times 3 all over 3 times 2 times 1. And we would have, if we do some cancellations, we would have 120 times 10, or 1200 ways that this could be done. I'm going to press pause for just a moment, and I'm going to get a new page, and we'll talk briefly about probability, and then you should have enough notes so that you are able to do the homework. So just a second, I'm going to press pause, and then okay, so for probability, this is section 11.8, and there is a difference between experimental probability and theoretical. In experimental probability, we're making some observations, we're gathering data. Maybe it's a coin toss, and so you're tossing this coin maybe 10 times, and you're writing down the number of times it lands with the tails showing. Whereas in theoretical, it's determined more by mathematical reasoning, that it should be equally likely that the coin would land heads or tails, and so we would expect that 1/2 of the time it would land with tails showing. If we do an experiment enough times, then it should be that our sample space has been increased, and so we should come closer to our theoretical probability. So in an experimental probability, if an event E occurs m times, now look how nice the pen is, out of n observations, then the experimental probability of this event, and we'd write it this way, would be m over n. Each of the outcomes, each time we do the experiment, a possible result is an outcome, and all these possible outcomes would give us our sample space. So an event is a subset of the sample space. In theoretical probability, if an event E can occur m ways out of the n possible equally likely outcomes, then the theoretical probability is m over n. So in the first example, if I'm going to want to find the probability of rolling either a 2 or a 3, from a standard die, then it would be 1/3, because there's 6 different outcomes. 2 of them are the outcomes I'm looking for, either a 2 or a 3, and so the probability would be 1/3. Let's suppose that we have, in my second example here, that we have a deck of cards, and it's a standard deck, so there's 52 cards, and we're going to select 4, or draw 4. So 4 are drawn. And the deck is well shuffled, and we want to know what's the probability that they will all be red. So the probability of drawing 4 cards would be 52 choose 4. And the number of ways of drawing 4 cards out of this standard deck would be 52 choose 4. The number of ways of choosing 4 red cards, since there are 26 that are red, it would be 26 choose 4. Well, the probability then would be of this event occurring would be 26 choose 4 over 52 choose 4. And the numerator would be 26 factorial over 4 factorial times 22 factorial. And this is divided by 52 factorial over 4 factorial and times 48 factorial. Well, that would be simplified to 26 factorial times 48 factorial all over 22 factorial times 52 factorial. Well, 26 factorial divided by 22 factorial would just be 26 times 25 times 24 times 23, and 48 factorial divided by 52 factorial would be 52 times 51 times 50 times 49. And then if we simplify, we would have 46 over 833. Now, if we had one more example, if we had a group of 10 men and we had 10 women, me make that a little better as a 10 here. And so we have 10 women, 10 men and 10 women. And 4 people are to be selected at random. So the number of ways to select 4 would be 20, because there's a total of 20 people. Choose 4. Now, if we want the number of ways to select 2 men and 2 women, then it would be, and you can see my pen's getting sloppy again, 10, choose 2 for the men, and the same thing for the women. And if we simplify that out, we would have 135 over 323, because it would be 10 factorial over 2 factorial times 8 factorial for both the men and the women. Whoops, that doesn't look very good. And again, I apologize for the pen. And then that's going to be divided by 20, choose 4, which would be our, and we'll take a reciprocal and multiply, so it's going to end up being multiplied by 4 factorial times 16 factorial all over 20 factorial. And I'll let you to simplify that, and then you can see that we get 135 over 323. Well, I hope this information has reminded you of some of the concepts you've heard before. I hope you've been able to read the work, and I'll see you in class soon. Take care. Bye-bye.